Look around you, and almost everything you see exists because of light. Every sunrise, every distant star, every galaxy shining across the cosmos depends on photons that have survived incredible journeys. Yet hidden behind that familiar glow is a mystery that stretches across the entire history of the universe. The first light emerged billions of years ago, and since then an unimaginable number of photons have flooded space in every direction. But where are they now? Are they still racing through the darkness? Can a photon outlive the star that created it, the galaxy that released it, or even the universe itself? Somewhere across the expanding cosmos, ancient light from forgotten eras is still traveling toward destinations no observer may ever witness. Tonight, we explore one of the deepest questions in cosmology, the hidden fate of every photon ever created, and whether light truly has an ending. It is easy to think of light as something ordinary. Sunlight pours across Earth every morning. Stars shine in the night sky. Galaxies glow through the lenses of powerful telescopes. Light feels so familiar that we rarely stop to consider how extraordinary its existence truly is. Every beam of sunlight reaching your face, every star visible in the darkness, and every distant galaxy captured by astronomers is part of a story that began billions of years ago. The universe was not always filled with light. There was a period in cosmic history when light could not travel freely at all. Shortly after the Big Bang, the universe was unimaginably hot and dense. Matter did not exist in the form of stars, planets, or galaxies. Instead, reality resembled an immense ocean of energy and particles packed so tightly together that photons constantly collided with everything around them. Light existed, but it could not move very far. Every attempt to travel was interrupted by another interaction. The universe was filled with radiation, yet strangely opaque. Imagine standing inside an endless fog so thick that visibility extends only a few centimeters. Light may be everywhere, but it cannot carry information over long distances. The early universe behaved in a similar way. Photons were trapped within a dense environment that prevented them from moving freely through space. As the universe expanded, however, everything began to change. Temperatures slowly decreased. Matter cooled. The density of particles dropped. Eventually, after hundreds of thousands of years, conditions became calm enough for electrons and atomic nuclei to combine into stable atoms. For the first time, photons could travel enormous distances without constantly crashing into charged particles. This event transformed the cosmos. Suddenly, light was released. A vast flood of ancient photons began racing outward in every direction. Those photons still exist today. Scientists can detect them. They form what is known as the cosmic microwave background, a faint sea of ancient radiation filling the entire observable universe. Every direction we look reveals traces of this primordial light. It is the oldest light humanity has ever observed, carrying information from a time when the universe was only a tiny fraction of its current age. Yet this ancient radiation represents only the beginning of the story. As the first stars ignited, new floods of photons entered the cosmos. Deep within stellar cores, nuclear fusion transformed matter into energy. Enormous quantities of light escaped into surrounding space. Every star became a factory producing unimaginable numbers of photons every second. The scale of this production is almost impossible to grasp. Our sun alone releases roughly 400 septillion watts of energy. Every second, countless photons stream away from its surface, beginning journeys that may continue for billions of years. Multiply that by the hundreds of billions of stars in the Milky Way, and then multiply again by the hundreds of billions of galaxies scattered throughout the observable universe. The result is a cosmic flood beyond ordinary comprehension. For billions of years, stars have continuously filled the universe with light. Every stellar birth contributes new photons. Every supernova explosion releases vast torrents of radiation. Every galaxy becomes a source of illumination. The cosmos has spent much of its history generating an enormous ocean of traveling light. What makes this particularly fascinating is that photons rarely remain near the places that created them. The moment a photon escapes its source, it begins an independent journey through space-time. A photon emitted by a star does not carry loyalty to that star. It does not orbit it forever. It departs. Some photons reach nearby planets. Some are absorbed by interstellar dust. Some collide with atoms and disappear into new physical processes. Others continue traveling across unimaginable distances. Many photons produced billions of years ago are still moving through the universe today. They have outlived the stars that created them. They have crossed regions of space larger than entire galaxies. They continue racing through darkness long after their origins have faded into history. This introduces one of the most remarkable facts about light. A photon can survive far longer than the object that produced it. Imagine a star forming, shining for millions of years, and eventually dying in a spectacular explosion. The star disappears. Its planetary system may be destroyed. Its local environment may transform completely, yet some of the photons released during that star's lifetime continue traveling. The source becomes history. The light remains. Photons act like cosmic messengers carrying traces of vanished eras. They preserve information about events that no longer exist. Every photon arriving at a telescope carries evidence of a moment in the past. When astronomers observe distant galaxies, they are not seeing those galaxies as they are now. They are seeing photons that began their journeys millions or billions of years ago. The universe therefore contains a vast archive of traveling history. Ancient photons move through space carrying records of stars that have died, galaxies that have evolved, and cosmic environments that no longer exist in their original form. The deeper we think about this reality, the more astonishing it becomes. The night sky is not merely a collection of distant lights. It is a flood of ancient travelers. Every visible star sends photons toward us. Every galaxy contributes its own stream of radiation. Every direction contains light from different eras of cosmic history. The universe is filled with photons from countless generations of stars, many of which disappeared long ago. And despite all the light that has already been produced, the story is far from over. Even now, new stars continue forming. New photons continue being released. New journeys begin every second. The cosmic flood has been expanding for billions of years, filling space-time with an ever-growing population of ancient travelers whose destinies stretch far beyond the lifetimes of the objects that created them. Which raises an extraordinary question. If the universe has been producing photons for nearly its entire history, and if many of those photons can survive for billions of years, where exactly are they now? Because somewhere beyond the stars, we can see lies an immense population of ancient photons still racing through the darkness, traveling toward destinations that may never contain an observer waiting for their arrival. They usually imagine something visible, a glowing star, a bright lamp, a distant galaxy shining through a telescope, or sunlight reflecting from a familiar landscape. Because human vision depends on light, it feels natural to assume that if photons exist, they should eventually be seen by someone or detected by something. The universe tells a very different story. Most photons are never observed by anyone. Many have traveled for billions of years without encountering a single eye, telescope, planet, or detector. Some were released before Earth even existed. Others began their journeys before the sun was born. Countless photons continue crossing the cosmos in complete darkness, carrying information from ancient times toward destinations that may never contain an observer. This creates one of the most fascinating realities in cosmology. The universe is filled with ancient light that nobody has ever seen. To understand why, imagine standing on a shoreline at night and throwing a bottle into the ocean. The bottle drifts away with the currents. Perhaps it reaches another shore. Perhaps someone eventually discovers it, but most likely it continues wandering through the water without ever being found. Now imagine not one bottle, but trillions upon trillions of bottles released continuously over billions of years into an ocean larger than imagination can grasp. Most would never be recovered. Most would simply continue drifting. Photons experience something remarkably similar. Every star releases enormous numbers of photons into space. These photons spread outward in all directions, Some strike nearby planets, some are absorbed by clouds of gas and dust, some interact with atoms inside galaxies, yet an enormous fraction escape into the vast emptiness between cosmic structures. Once they enter those regions, their journeys can become extraordinarily long. The distances separating galaxies are almost impossible to visualize. Light requires years to cross the space between stars. It requires millions of years to travel between neighboring galaxies. It may require billions of years to move across significant portions of the observable universe. Throughout those journeys, many photons encounter nothing at all. Space is often described as empty, and while that description is not perfectly accurate, it captures an important truth. The average density of matter across enormous cosmic distances is astonishingly low. A photon can travel through intergalactic space for unimaginable periods without colliding with anything. The result is a universe crowded with travelers, but largely devoid of destinations. This is one reason ancient photons are so difficult to find. Many simply never arrive anywhere useful. They continue moving through darkness, carrying information that may never be read. One of the most remarkable examples comes from the earliest visible light in cosmic history. After the young universe cooled enough to become transparent, a tremendous flood of radiation spread throughout space. Those photons have been traveling ever since. Today, scientists detect them as the cosmic microwave background, a faint glow filling the entire sky. Yet even this famous radiation illustrates the larger mystery. The photons we detect represent only a tiny fraction of all those ancient travelers. Countless others continue moving through the cosmos without ever crossing paths with our instruments. The universe contains far more ancient light than humanity has ever measured. Another reason these photons remain hidden involves the expansion of space itself. As photons travel across the universe, they do not move through a static environment. The cosmos expands while they journey. Distances grow, the structure of space-time changes, the path ahead evolves continuously. This expansion has an important effect on light. It stretches wavelengths. A photon that began as visible light can gradually become infrared radiation. Given enough time, infrared light can become microwave radiation. The stretching continues as the universe grows. Ancient photons may possess wavelengths so large and energies so low that detecting them becomes extraordinarily difficult. The photon still exists. The journey continues. Its visibility fades. Imagine hearing a musical note that slowly becomes lower and lower in pitch. At first, it remains obvious. As the frequency decreases, the sound becomes harder to hear. Eventually, it drops below the range of human hearing altogether. The note has not disappeared. Your ability to detect it has. Something similar happens to many ancient photons. They continue traveling while becoming increasingly difficult to observe. The universe slowly transforms bright signals into faint whispers. This creates a remarkable situation. The cosmos may contain enormous populations of photons that are effectively invisible to us, not because they are absent, but because expansion has altered their properties over billions of years. Another fascinating aspect of this mystery is that photons do not need to remain near their origins. Human beings often associate objects with locations. A tree grows where it is rooted. A mountain remains where it formed. Even planets typically stay within their star systems. Photons are different. Once released, they become independent travelers. A photon emitted from a star billions of years ago may now occupy a region completely unrelated to its birthplace. The star may have died. Its galaxy may have evolved dramatically. Entire cosmic environments may have transformed. The photon continues onward. Ancient light becomes separated from its own history. This means the universe contains vast numbers of photons whose origins are effectively lost. They still carry information about where they came from, yet no observer may ever recover that information. The message survives. The reader never arrives. The deeper we think about this reality, the stranger it becomes. Human beings often imagine observation as central to existence. We tend to focus on what can be seen, measured, or detected. Yet most of the light ever produced may spend its entire existence beyond observation. Photons travel. The universe expands. Distances grow. The journeys continue. Meanwhile, countless ancient messengers cross the cosmos without witnesses. The most astonishing realization is that some of these photons are older than galaxies as we know them today. Some began moving through space when the universe looked completely different from its present form. They have survived cosmic expansion, the birth and death of stars, the formation of planets, and the evolution of entire galactic structures. Still they travel. Still they move through darkness. Still they carry traces of forgotten eras. And yet many of them may never be found, not because they have vanished, not because they have been destroyed, but because the universe is so vast, so old, and so continuously expanding that countless photons spend their entire existence wandering through space-time without ever encountering an observer capable of recording their arrival, which leads to an even deeper mystery. If so many photons survive long after their sources disappear, what exactly happens to light after the star, galaxy, or event that created it has already become part of the distant past? They usually connect it to the object that produced it. Sunlight belongs to the sun. Starlight belongs to stars. The glow of a distant galaxy belongs to the billions of stars shining inside it. In everyday experience, the source and the light appear inseparable because they are observed together. We look at a lamp and see the light coming from it. We look at a star and see its brightness filling the sky. The universe reveals a much stranger reality. A photon's journey does not end when it leaves its source. In many cases, that journey is only beginning. Once a photon escapes from a star, a supernova, a quasar, or any other cosmic event, it becomes an independent traveler. It no longer depends on the object that created it. The star may continue shining for millions of years, or it may disappear tomorrow. The galaxy may evolve into something completely different. Entire regions of space may transform beyond recognition, yet the photon continues moving through the cosmos, carrying with it a small fragment of history from a moment that may never occur again. This creates one of the most remarkable situations in nature. Light can survive long after its source has vanished. Imagine receiving a letter written hundreds of years ago. The person who wrote it is gone. The city where it was written may have changed completely. The world that existed when the letter was created has disappeared into history, yet the message survives. It carries information from a time that no longer exists. Photons behave in a surprisingly similar way. Every beam of light contains evidence of the conditions present at the moment it was released. The light remembers the temperature of the star that produced it. It carries clues about the chemical elements found within its source. It preserves information about the environment from which it escaped. As long as the photon continues traveling, that information continues existing. The source may disappear. The message remains. This idea becomes especially powerful when we look into the night sky. Many of the stars visible to the naked eye are relatively close by cosmic standards, meaning their light reaches us within years or decades. Yet when astronomers observe distant galaxies, they often see light that began its journey millions or even billions of years ago. That means the photon arriving today started traveling before countless events in cosmic history had occurred. Entire generations of stars formed and died while the photon was in transit. Galaxies changed shape. Black holes grew larger. Planetary systems emerged. Civilizations may have appeared and vanished. Throughout all of these transformations, the photon continued its journey uninterrupted. The deeper we think about this, the stranger it becomes. Imagine a massive star nearing the end of its life. For millions of years it shines brilliantly, releasing enormous numbers of photons into surrounding space. Eventually, the star exhausts its fuel and explodes as a supernova. The explosion may destroy nearby planets and dramatically alter its local environment. The star's existence comes to an end. Yet countless photons released during its lifetime continue moving through the universe. Some may travel for billions of years after the star itself has vanished. In a sense, the light becomes a survivor of a world that no longer exists. The cosmos is filled with these survivors. Every direction in space contains photons whose origins belong to distant chapters of cosmic history. Some come from stars that disappeared long ago. Some originate from galaxies that have evolved beyond recognition. Others began their journeys when the universe itself was far younger than it is today. The photons continue moving, even though the circumstances that created them have become part of the past. Another fascinating aspect of this hidden journey is that light rarely follows a simple path. Popular illustrations often show photons moving across empty space in perfectly straight lines, traveling from one point to another without interruption. Reality is often more complicated. A photon may pass through clouds of interstellar gas. It may encounter magnetic fields. It may travel near massive galaxies whose gravity bends the surrounding space-time. It may cross enormous cosmic structures stretching across millions of light years. Throughout this journey, the photon remains part of an evolving universe. The environment around it changes constantly, yet the photon continues carrying information from its origin. This is one reason astronomers value light so highly. Nearly everything we know about the distant universe comes from photons. Scientists cannot visit remote galaxies, they cannot travel to ancient stars, they cannot physically explore the early universe. Instead, they study the messages carried by light. Every photon arriving at a telescope serves as a messenger from another place and another time. The photon's hidden path becomes a bridge connecting the present to the distant past. What makes this bridge extraordinary is that it often outlasts the structures it describes. A galaxy may change dramatically after releasing a photon. A star may disappear. A nebula may collapse into new stars. The photon preserves evidence of an earlier moment. It becomes a moving archive, a record traveling through space-time. The most astonishing consequence of this process is that the universe is filled with information from vanished eras. Ancient photons crossing the cosmos right now contain evidence of environments that no longer exist. They are like fragments of history wandering through darkness, carrying stories from places transformed by billions of years of cosmic evolution. Many of these photons will never be detected. Many will never encounter an observer, yet the information remains embedded within them. The message survives whether or not someone reads it. This reveals a profound truth about light. A photon is not merely illumination. It is a memory. Every photon carries a trace of where it came from. Every photon preserves a connection to a moment that once existed. And as long as it continues traveling, that moment remains encoded within its journey. But there is another force shaping the destiny of these travelers. Even if a photon survives for billions of years, the universe through which it moves does not remain unchanged. Space itself continues expanding, stretching the very fabric of reality. And because of that expansion, the fate of light becomes tied to something far larger than the stars that created it. The next mystery is not whether photons survive after their sources disappear. The next mystery is how the expansion of the universe gradually transforms every photon that continues its endless journey through space. When people imagine a photon traveling through the universe, they often picture a simple journey. A star emits light. The photon races through darkness. Eventually it reaches a planet, a telescope, a cloud of gas, or perhaps continues onward forever. The path appears straightforward, almost mechanical. The photon moves, and space merely serves as the empty stage through which the movement occurs. For centuries, this was close to how many people imagined the cosmos itself. Space seemed passive. Stars moved through it, galaxies occupied it, light crossed it. Yet the space in between appeared unchanged. Modern cosmology has revealed something far stranger. Space is not a static background. Space evolves. Space expands. Space participates in the story. And because every photon must travel through space, the evolution of the universe becomes part of the photon's destiny. This realization transformed our understanding of light. A photon does not simply move through the cosmos. It moves through a cosmos that is changing while the journey takes place. To appreciate how remarkable this is, imagine sending a ship across an ocean. Under ordinary circumstances, the ocean remains roughly the same size throughout the voyage. The ship departs, crosses the water, and eventually reaches its destination. The traveler changes position, but the ocean itself remains largely unchanged. Now imagine something very different. Imagine the ocean expands while the ship is crossing it. Every mile traveled creates additional miles ahead. The water itself grows larger during the journey. The destination remains the same. The route does not. The traveler must cross an environment that continuously transforms. The universe creates a similar situation for every photon. A photon leaving a distant galaxy today may spend billions of years traveling through space. During that immense span of time, the universe continues expanding. The distances between galaxies grow. The geometry of space-time evolves. The structure of reality changes. The photon moves. The cosmos changes around it. One of the most important consequences of this process involves wavelength. Light behaves both like a particle and a wave. Every photon possesses a wavelength which determines the type of light it represents. Short wavelengths correspond to high-energy radiation such as gamma rays. Longer wavelengths correspond to lower energy forms such as radio waves. When a photon begins its journey, its wavelength reflects the conditions of its source. A hot star may produce visible light. An energetic explosion may release gamma rays. A cooler object may emit infrared radiation. At the moment of creation, the photon's wavelength carries information about where it came from. The expanding universe gradually alters that information. As space grows, the wavelength stretches. The photon itself continues traveling at the speed of light, yet the wave associated with the photon becomes longer. Imagine drawing a series of evenly spaced marks on a rubber band. If the rubber band stretches, the marks move farther apart. The pattern remains, but the spacing changes. Cosmic expansion affects light in a surprisingly similar way. The universe stretches the wavelength of traveling photons. This phenomenon is known as cosmological redshift. It represents one of the most powerful pieces of evidence that the universe is expanding. The farther a photon travels through the expanding cosmos, the greater the stretching becomes. A photon that began as visible blue light may eventually become red light. Given enough time, red light may become infrared radiation. Infrared radiation may become microwaves. The process continues as the universe evolves. The photon survives. Its character changes. This means that space itself gradually reshapes the identity of every photon. The source may remain the same. The journey transforms the traveler. One of the most fascinating examples of this process involves the oldest light in the universe. Shortly after the cosmos became transparent, an enormous flood of radiation filled space. At that time, the radiation possessed far higher energy than it does today. For billions of years, those photons traveled through an expanding universe. The wavelengths stretched, the energy decreased, the radiation changed. Today, that ancient light survives as the cosmic microwave background. The photons still exist, yet they look dramatically different from the way they appeared when they began their journeys. Space itself transformed them. This reveals something extraordinary. The universe does not merely transport light, it modifies light. Every photon becomes part of an ongoing interaction with the expanding cosmos. Another remarkable consequence involves energy. When wavelengths stretch, photon energy decreases. This creates one of the most intriguing questions in cosmology. Where does the energy go? The answer remains surprisingly subtle. The universe does not behave like ordinary systems where energy simply transfers from one location to another. On cosmic scales, the expansion of space-time changes the framework within which energy is defined. The photon loses energy as its wavelength grows. The change reflects the evolving geometry of the universe itself. Expansion quietly drains energy from light throughout cosmic history. A photon released billions of years ago may carry far less energy today than when it began its journey. The traveler survives. The cargo becomes lighter. What makes this especially profound is that the process affects every photon crossing vast distances. No star can prevent it. No galaxy can avoid it. No civilization can reverse it. Expansion acts upon light universally. Every ancient photon becomes a witness to the growth of spacetime. The deeper astronomers studied redshift, the more they realized that photons provide a record of cosmic expansion itself. By measuring how much light has stretched, scientists can estimate how much the universe has grown during the photon's journey. Each photon becomes more than a messenger from a distant source. It becomes a messenger from the history of spacetime. The light carries information not only about where it originated, but also about what happened during its voyage. Its wavelength preserves evidence of the universe's evolution. This transforms photons into some of the most valuable tools in cosmology. Every ancient beam of light contains clues about the growth of the cosmos. Every stretched wavelength reveals something about the changing structure of reality. Every photon arriving at a telescope carries a history written across billions of years of expansion. Yet the story becomes even stranger when we consider the far future. The universe is not merely expanding. The expansion appears to be accelerating. This means that future photons will travel through an environment becoming increasingly stretched. The distances will grow faster. The wavelengths will lengthen further. The energies will continue declining. Ancient light will become increasingly diluted across an ever larger cosmos. Some photons may eventually possess wavelengths so enormous that they become almost impossible to detect. The photons continue existing. The universe gradually transforms them into faint echoes of their former selves. This is the deepest lesson hidden within the destiny of light. A photon's future is not determined solely by the object that created it. The star may vanish, the galaxy may disappear, the source may become ancient history. Yet another force continues shaping the photon's fate long afterward. The expansion of space itself, an invisible process unfolding across the entire cosmos, a process that stretches wavelengths, reduces energies, and slowly reshapes every beam of light traveling through reality. And as that transformation continues for billions upon billions of years, it leads to an even more mysterious consequence. The universe does not merely change the appearance of light, it slowly drains something from it. A subtle process that affects every ancient photon crossing the cosmos and raises one of the most fascinating questions in modern cosmology. What exactly happens when the energy of light continues fading across an expanding universe that never stops growing? The most remarkable fact about light is that it seems almost immortal. A photon can survive journeys lasting billions of years. It can cross enormous regions of space without colliding with anything. It can outlive stars, outlast galaxies, and continue traveling long after the events that created it have disappeared into history. Compared with nearly every other structure in the universe, light appears extraordinarily durable. Yet hidden inside this apparent endurance is a slow transformation that affects every photon crossing the cosmos. The photon survives. Its energy does not remain the same. As light travels through the expanding universe, something unusual happens. The photon is not destroyed. It is not absorbed. It is not broken apart into smaller pieces. Instead, it gradually loses energy through one of the strangest processes known in cosmology. The expansion of space itself slowly drains energy from light. This idea sounds almost impossible at first because human intuition treats energy as something that remains attached to an object. A moving car possesses energy because it moves. A heated object contains energy because its particles vibrate. A beam of light carries energy because it consists of photons. If the photon survives, it seems natural to assume that its energy should survive unchanged as well. The universe behaves differently. To understand why, imagine a musician plucking a guitar string. The vibration produces a specific note. If the string were somehow stretched while still vibrating, the character of the sound would change. The frequency would shift, the note would become lower, the vibration would survive, its energy would be altered. The expanding universe creates something similar for light. Every photon possesses a wavelength and a frequency. These properties determine how much energy the photon carries. Short wavelengths correspond to higher energies, long wavelengths correspond to lower energies. As space expands, wavelengths stretch. The photon continues traveling. Its wavelength becomes larger. Its frequency becomes lower. Its energy decreases. This process is known as cosmological redshift, and it is one of the most important discoveries in modern astronomy. When astronomers observe distant galaxies, they find that the light arriving from those galaxies has been stretched during its journey. The farther the light has traveled, the more dramatic the stretching becomes. The photon reaching Earth today may look very different from the photon that originally left its source. A beam of blue light may become red. Visible light may become infrared radiation. Infrared radiation may become microwaves. The transformation continues as the universe grows. What makes this process so fascinating is that nothing directly attacks the photon. There is no cosmic obstacle draining energy from it. No invisible cloud absorbs part of its power. No collision robs it of strength. The photon loses energy simply because the universe expands while it travels. Space itself becomes responsible for the change. This raises one of the most intriguing questions in cosmology. Where does the energy go? In everyday situations, energy conservation feels straightforward. If a moving object slows down, the energy often transfers elsewhere. Friction generates heat. Motion becomes sound. Energy changes form but remains within the system. The expanding universe creates a more subtle situation. The photon's energy decreases, yet there is no obvious destination for the missing energy. This puzzled scientists for many years and continues to challenge intuition even today. Part of the difficulty comes from the fact that the universe does not behave like a simple machine. On cosmic scales, space-time itself evolves. The rules governing energy become more complicated than they appear in everyday experience. The reduction in photon energy reflects the changing geometry of the universe rather than a transfer into some hidden reservoir. The expansion alters the framework within which energy is measured. The photon's loss is tied directly to the growth of spacetime. The universe itself participates in the process. The deeper we think about this phenomenon, the more extraordinary it becomes. Imagine a photon released by a distant galaxy billions of years ago. At the moment of its creation, it may have possessed far more energy than it carries today. The galaxy emitted it into a younger universe, one that was smaller and denser than the cosmos we currently inhabit. For billions of years, the photon traveled. During that time, stars formed and died. Galaxies collided. Black holes grew. Entire cosmic structures evolved. The photon survived every one of these changes. Yet while surviving them, it slowly surrendered energy to the expansion of reality itself. By the time it reaches a telescope on Earth, it may carry only a fraction of the energy it once possessed. The traveler remains. The journey has transformed it. One of the most striking examples of this process involves the oldest light in existence. The cosmic microwave background began its journey when the universe was only about 380,000 years old. At that time, the radiation filling space was far more energetic than the microwave scientists detect today. Billions of years of expansion stretched those wavelengths enormously. The photons survived. Their energies diminished. What was once intensely energetic radiation gradually became a faint microwave glow spread across the sky. Without expansion, the cosmic microwave background would look entirely different. The universe itself changed the character of its oldest light. This realization reveals that photons are not merely messengers carrying information from distant places. They are also witnesses to cosmic history. Every reduction in energy records part of the universe expansion. Every stretched wavelength contains evidence that space-time has grown during the photon's journey. The light arriving today carries two stories simultaneously. One story describes its source. The other describes the evolution of the universe through which it traveled. Another fascinating consequence emerges. when we think about the future. The universe is not only expanding, observations suggest that expansion is accelerating. This means the stretching of wavelengths will continue. Future photons crossing immense distances will experience even more dramatic transformations. Light emitted by stars today will gradually lose energy as it moves through an ever-growing cosmos. The process never pauses, the stretching never stops. The reduction continues for as long as the photon survives. Imagine a traveler walking across a landscape that continuously becomes larger. Every step covers less of the total journey than the step before. The destination grows more distant. Progress becomes increasingly diluted by the expanding terrain. Ancient photons experience something similar. Their wavelengths stretch across a growing universe. Their energies become increasingly diluted. Their identities slowly change. Yet the photons themselves continue onward. This creates one of the most poetic realities in cosmology. Light does not age in the way stars age. It does not burn fuel. It does not wear out. It does not decay simply because time passes. The universe changes around it. The cosmos reshapes the photon's destiny through expansion, a slow transformation unfolding across billions of years, a process so gradual that no individual photon notices it, yet so powerful that it can turn brilliant radiation into faint whispers crossing the darkness. And eventually this process leads to an even stranger outcome. Some photons travel for so long, through such vast stretches of expanding spacetime, that they enter regions where they become effectively lost forever, not destroyed, not absorbed, not ended, simply carried so far into the expanding cosmos that their journeys continue beyond every realistic possibility of observation. A fate that raises the next great mystery in the story of light. If photons can survive while continually losing energy, what happens when ancient light drifts into regions of the universe from which it can never return? They often picture a successful journey. A star emits a photon. The photon crosses the darkness. Eventually it reaches a planet, a telescope, a cloud of gas, or some other destination where its story comes to an end. This picture feels natural because nearly every example of light we encounter in daily life follows a similar pattern. Light leaves a source and eventually arrives somewhere. The universe contains a much stranger possibility. Some photons may spend their entire existence traveling without ever reaching a meaningful destination. Others may enter regions of the cosmos from which their information can never return. Still others may continue moving through space long after every realistic opportunity for observation has disappeared. In this sense, the universe contains places where ancient light becomes lost forever. Not destroyed, not erased, not absorbed, lost in a much deeper way. Lost through separation, lost through distance, lost through the expanding architecture of the cosmos itself. To understand why this happens, it helps to think about what a photon actually requires in order to be observed. A photon can exist perfectly well on its own. It does not need an observer to survive. It does not require a destination to continue traveling. Yet for its information to matter to another part of the universe, the photon must eventually interact with something. It must reach a detector. It must strike an atom. It must encounter matter capable of receiving its message. Without such an encounter, the photon simply continues moving. The message survives. The recipient never arrives. Imagine placing a letter into a bottle and throwing it into an immense ocean. The bottle drifts away. Years pass. Decades pass. Centuries pass. The message remains sealed inside. The information survives. Yet if the bottle never reaches a shore, never encounters a ship, and never arrives at a place where someone can open it, the message becomes functionally lost. The words still exist. The communication never occurs. Ancient photons often experience a similar fate. The cosmos is unimaginably large. Even the observable universe contains distances measured in billions of light years. Between galaxies lie enormous regions where matter is extraordinarily sparse. A photon can travel through these vast stretches for periods far exceeding the lifespan of stars, planets, or civilizations. Many photons spend their existence crossing regions where almost nothing exists to receive them. This situation becomes even more remarkable when cosmic expansion enters the picture. The universe is not static. The distances between many galaxies continue increasing. The fabric of space-time stretches. Regions that were once capable of exchanging information gradually drift apart. Some photons find themselves moving through a cosmos that continuously becomes more difficult to cross. Imagine walking toward a distant city while the landscape itself expands beneath your feet. You continue moving forward, yet the destination grows more distant. The route lengthens during the journey. The universe creates an analogous challenge for light. The photon moves at the speed of light. Space itself expands. The future relationship between the photon and potential destinations changes. One of the most important consequences of this process involves what cosmologists call the cosmic event horizon. This horizon is not a physical wall. It is not a barrier floating somewhere in space. It represents a limit on future communication. Beyond certain distances, expansion can become so significant that information emitted today will never successfully reconnect with particular regions. The photon survives. The opportunity for future interaction disappears. This means there are photons traveling through the universe right now that may never become part of any future observation. Their journeys continue. Their messages remain intact, yet the destinations capable of receiving them drift permanently beyond reach. The deeper scientists studied this idea, the stranger it became. Human beings often think of being lost as a temporary condition. A lost traveler may eventually find a path. A lost ship may eventually locate a harbor. A lost signal may eventually reach a receiver. Cosmic loss can be permanent. The photon continues existing. The possibility of arrival vanishes. This distinction transforms the way we think about light. A photon does not need to be destroyed to become unreachable. It only needs to become disconnected from every future observer. Another fascinating aspect of this process involves the ancient light released during earlier eras of cosmic history. Countless stars have existed throughout the life of the universe. Many burned brightly for millions or billions of years before disappearing. Every one of those stars released enormous numbers of photons. Some of those photons reached planets. Some were absorbed by dust. Some contributed to the formation of new structures. Yet vast numbers escaped into intergalactic space. Many continue traveling today. Their stars are gone. Their galaxies have evolved. Their local environments have changed beyond recognition. The photons remain. The information they carry survives. Yet much of that information may never again become accessible. The photons drift through regions growing increasingly isolated from the rest of the cosmos. This creates an extraordinary image of the universe. Reality becomes filled with ancient messengers carrying stories from forgotten times. Messages from stars that no longer exist. Messages from galaxies transformed by billions of years of evolution. Messages from cosmic environments that vanished long ago. The messages survive. The recipients may never exist. One reason this idea feels so unsettling is that human beings instinctively connect information with purpose. A message exists to be received. A signal exists to be detected. A photograph exists to be viewed. The universe imposes no such requirement. Photons can carry information forever without anyone ever reading it. Their existence does not depend upon observation. Their journeys do not require witnesses. The cosmos may contain an immense archive of inaccessible history, a vast collection of ancient information moving through darkness beyond every realistic possibility of recovery. The archive remains. The access disappears. This realization becomes even more profound when we think about the far future. As expansion continues, more regions of the universe drift beyond communication. More destinations become inaccessible. More photons find themselves crossing increasingly isolated domains. The number of unreachable journeys grows. The number of disconnected messages increases. The universe gradually transforms into a place where ancient light survives, while opportunities for observation diminish. Photons continue their voyages. The network of communication shrinks. The darkness between regions expands. The most remarkable aspect of all is that these photons are not rare exceptions. The universe may contain unimaginable numbers of them. Every galaxy has contributed to the population. Every star has released its own flood of radiation. Every age of cosmic history has added new travelers to the expanding sea of space-time. Many will never return. Many will never arrive. Many will continue moving through reality long after the structures that created them have disappeared. And somewhere among those ancient travelers are photons that may ultimately outlive not only stars and planets, but entire galaxies themselves. Photons whose journeys continue across spans of time so immense that the galaxies which produced them become distant memories in cosmic history, which leads to an even more astonishing question. What happens when a single photon survives longer than the galaxy that created it, longer than the stars surrounding it, and longer than entire chapters of cosmic evolution? What becomes of light when it begins to outlive the very structures that once defined its origin? Human beings naturally think of light as temporary. A candle burns for a while and then goes dark. A flashlight shines until its battery is exhausted. Even the sun, which appears eternal from the perspective of a human lifetime, is ultimately a finite object. One day it will run out of fuel and undergo a dramatic transformation. In everyday experience, light seems tied to the lifespan of whatever produces it. The universe reveals a far stranger possibility. A photon can survive long after the object that created it has disappeared. A photon can continue traveling for such immense periods of time that it outlives not only individual stars, but entire galaxies. This idea is difficult to appreciate because galaxies already seem ancient beyond imagination. The Milky Way has existed for billions of years. Countless generations of stars have been born and died within it. Entire chapters of cosmic history have unfolded during its lifetime. Compared to the lifespan of civilizations, planets, or even stars, galaxies appear almost permanent. Yet galaxies are not eternal. They evolve, they collide, they transform. They gradually change over immense stretches of time. Photons, under the right circumstances, can continue their journeys throughout all of those changes. Imagine a traveler leaving a city and beginning a journey across a vast continent. The traveler continues walking for centuries. During that time, the city expands, changes its architecture, develops new cultures, and eventually becomes something entirely different from the place that existed when the journey began. The traveler remains on the road. The city becomes history. A photon can experience something remarkably similar on cosmic scales. Consider a star living inside a distant galaxy billions of years ago. Deep within its core, nuclear fusion releases tremendous amounts of energy. Some of that energy escapes into space in the form of photons. One of those photons leaves the star and begins traveling through the cosmos. Nothing about the journey seems unusual. The photon crosses the space surrounding its star. It leaves its local stellar neighborhood. It enters the wider galaxy. Time continues moving forward. Millions of years pass. The star evolves. Its internal structure changes. Its future unfolds. The photon continues traveling. The star reaches the end of its life. Depending on its mass, it may collapse into a white dwarf, explode as a supernova, or become a neutron star or black hole. The object that produced the photon ceases to exist in its original form, yet the photon survives. Its journey continues. The source becomes part of history. The messenger remains. The story becomes even more extraordinary when we expand our perspective from stars to galaxies. Galaxies are not static structures. They grow through mergers. They consume smaller galaxies. Their shapes evolve. Their populations of stars change continuously. Entire regions may transform beyond recognition over billions of years. The Milky Way itself will not remain as it is today. Astronomers predict that it will eventually collide with the neighboring Andromeda galaxy. The two vast stellar systems will merge, creating a completely new galactic structure. When that event occurs, The night skies of countless worlds will be transformed. The architecture of both galaxies will change. The cosmic environment will be rewritten. Yet photons released long before the merger may still be traveling through the universe. The galaxies evolve. The photons continue. This creates one of the most remarkable situations in nature. A photon can become older than the galaxy it remembers. Not older in the sense of age alone, but older in the sense that the galaxy which created it no longer exists in the form it once did. The photon's information preserves a snapshot of a vanished era. Its source has changed. Its message has not. Photons function like moving pieces of history. They carry evidence of places that no longer exist exactly as they once did. Every ancient photon becomes a record of a moment frozen in time. Astronomers encounter this phenomenon constantly when they observe distant objects. The light arriving at telescopes today often comes from galaxies that looked very different when the photons began their journeys. Entire generations of stars have formed since then. Galactic structures have evolved. Black holes have grown larger. The photons reveal the past. The galaxies have moved on. Another fascinating consequence emerges when we consider the immense emptiness of intergalactic space. A photon traveling through the sparse regions between galaxies may encounter almost nothing for billions of years. The density of matter in these regions is extraordinarily low. There are few obstacles, few interactions, and few opportunities for absorption. Some photons can survive astonishingly long journeys. They continue crossing the cosmos, while the structures around them undergo dramatic transformations. Stars die, galaxies merge, clusters evolve. The photon persists. Imagine a message sent across an ocean so vast that entire civilizations rise and fall before the letter reaches its destination. The societies that created the message may disappear, their languages may change, their cultures may vanish, yet the message survives. A photon can play a similar role in the universe. It becomes a traveler carrying information from a reality that no longer exists. This realization forces us to rethink the meaning of permanence. Human beings often view massive objects as enduring and light as fleeting. A mountain seems permanent compared to a flash of lightning. A galaxy seems permanent compared to a beam of light. On cosmic timescales, the comparison becomes more complicated. The mountain erodes. The star dies. The galaxy transforms. The photon continues moving. In some circumstances, the traveler becomes more enduring than the structures that launched it. The deeper implication is even more profound. A photon does not care whether its source survives. Its existence is independent. Once released, it follows its own path through space-time. The future of the star becomes irrelevant. The future of the galaxy becomes irrelevant. The photon's journey becomes a separate story. This separation between source and traveler reveals something fundamental about the universe. Creation and survival are not always linked. An object may disappear while its influence continues. A star may vanish while its light survives. A galaxy may transform while its ancient photons continue carrying evidence of what once was. Reality leaves traces of itself scattered across space-time. Those traces can endure far longer than the structures that produced them. The most astonishing possibility of all involves the far future. As the universe continues expanding, galaxies will drift farther apart. Many will become isolated from one another. Communication between distant regions will gradually disappear. Entire portions of the cosmos will become inaccessible. Yet photons released during earlier ages may continue traveling through those vast expanses long after galaxies have moved beyond contact, long after familiar cosmic structures have changed, long after the universe enters new eras of evolution. The photons remain. They become ancient witnesses crossing a cosmos that looks nothing like the one in which they were born. A photon can become a survivor of entire chapters of cosmic history, a messenger from vanished galaxies, a carrier of forgotten light, a traveler whose journey extends beyond the lifespan of the very structures that once defined its origin. And if photons can survive while galaxies transform around them, an even stranger question begins to emerge. What happens when those ancient travelers continue their journeys into a universe that itself is growing older, darker, and more isolated with every passing age? Because beyond the lifespan of galaxies lies another frontier entirely, the silent voyage of light through an aging cosmos whose future may be unlike anything we can observe today. They often focus on objects. They imagine the fate of stars, the evolution of galaxies, the growth of black holes, or the possibility of distant civilizations. These are the visible landmarks of cosmic history, the structures that give the universe its character and make it feel alive. Yet, while stars ignite and fade, while galaxies merge and drift apart, another story unfolds quietly in the background. It is the story of light itself. Photons do not build galaxies. They do not create planets. They do not shape civilizations. Instead, they travel, and in many cases, they continue traveling long after the objects that produce them have disappeared. As the universe grows older, the silent journeys of these photons become increasingly important because they may be among the last surviving traces of earlier cosmic eras. To understand why, imagine standing in an ancient city that has existed for thousands of years. Buildings rise and fall, roads change, entire generations come and go. The city constantly transforms, yet through all of those changes, messages continue moving through it. Letters are written, stories are told, records are preserved. Now imagine the city gradually emptying. The population shrinks, activity declines, the buildings have become older, the streets grow quiet, the messages continue moving. The messages become more numerous than the people still left to receive them. The aging universe may experience something surprisingly similar. Today, the cosmos remains rich with activity. Stars continue forming inside galaxies. New planetary systems emerge. Radiation floods space from countless sources. Every second, enormous numbers of photons are released into the universe. The future looks different. Astronomers believe the era of active star formation will not continue forever. Galaxies contain finite supplies of gas. Over immense stretches of time, much of that gas becomes locked inside stars, stellar remnants, or other structures. The raw material needed to create new generations of stars gradually becomes less abundant. As a result, the universe slowly changes character. The brilliant age of stellar creation begins to fade. The cosmos does not suddenly become dark. Rather, it grows quieter. The production of new light decreases. The population of ancient light continues traveling. This creates a remarkable situation. As the universe ages, an increasing fraction of its photons originate from events that occurred in the distant past. The light crossing space may become older than entire civilizations, older than planetary systems, older than some galaxies in their present form. Photons released during earlier eras continue moving through a cosmos that has already changed beyond recognition. One of the most fascinating aspects of this process is that photons themselves do not experience time in the way massive objects do. From the perspective of relativity, the journey of a photon is profoundly different from the experience of stars, planets, or living beings. A star ages, a galaxy evolves, a civilization develops and disappears. The photon simply travels. Its path stretches across the history of the universe while the universe changes around it. This means that ancient photons become witnesses to transformations occurring on scales far beyond ordinary comprehension. Imagine a message leaving a city at the height of an empire. The messenger begins traveling. While the journey continues, the empire expands, declines, collapses, and becomes part of history. The message survives all of it. The photon occupies a similar role in cosmic history. Its journey can span multiple eras of universal evolution. What makes this especially extraordinary is that the environment through which the photon travels never remains the same. The universe is not static. Space expands. Galaxies drift farther apart. Cosmic structures evolve. The large-scale architecture of reality changes continuously. The photon crosses all of it. Every ancient photon traveling today began its journey in a younger universe. The cosmos was smaller when it was released. Galaxies occupied different positions. The expansion of space had not yet reached its current scale. As billions of years pass, the photon moves through an environment becoming increasingly different from the one it originally knew. Light becomes a traveler moving not only through space, but through the changing conditions of cosmic history itself. Another remarkable consequence emerges when we consider the growing isolation of galaxies. As expansion continues, distant galaxies drift beyond one another's reach. Communication becomes more difficult. Entire regions of the universe gradually lose contact with one another, yet photons continue crossing these immense expanses. Even while galaxies separate, light attempts to bridge the growing distances. Many photons fail to complete that task. Some become trapped in the consequences of expansion. Others travel into regions where no observer will ever receive them. Still, they continue moving. Their journeys do not stop simply because communication becomes impossible. This reveals a profound distinction between existence and connection. The photon can survive even when relationships between cosmic regions disappear. The traveler continues. The network dissolves. The universe may therefore contain enormous populations of ancient photons wandering through increasingly isolated domains of spacetime. They become remnants of an earlier age when the cosmos was more connected than it will be in the future. One way to visualize this process is to imagine a library gradually losing readers. The books remain, their contents remain, the information survives, the audience becomes smaller. The future universe may resemble such a library. Ancient photons preserve information about earlier cosmic eras. They continue carrying evidence of stars, galaxies, and events that shaped the universe. Yet fewer and fewer destinations remain available to receive those messages. The information survives. The opportunities for observation decline. As the cosmos ages further, another transformation becomes increasingly important. The expansion of the universe continues stretching wavelengths. Ancient photons become less energetic. Visible light becomes infrared radiation. Infrared radiation becomes microwaves. Microwaves stretch into even longer wavelengths. The photons survive. Their energy diminishes. The universe gradually transforms bright signals into faint traces. This means that the aging cosmos becomes populated by travelers that are not only ancient but increasingly subtle. The messages continue existing while becoming harder to detect. The photon remains. Its voice grows quieter. The most haunting aspect of all is that many of these photons may never encounter another observer. They will continue traveling through darkness long after stars have faded from certain regions of the universe. They will cross expanses of space where no planets exist and no civilizations remain. Their journeys may continue through eras so distant that the universe itself seems unrecognizable compared to its present form. Yet they persist, carrying memories of earlier ages, preserving traces of forgotten stars, transporting information from galaxies that may no longer resemble the structures that created them. The silent journey of light becomes a thread connecting different chapters of cosmic history, a bridge between the youthful universe and the aging one, a reminder that while stars and galaxies evolve, photons can continue traveling across immense stretches of time, preserving echoes of the past long after the universe has moved on. And as this process continues, another question emerges. If ancient photons can survive into the distant future while the universe grows older and darker, what sources of illumination will remain when most of the stars we know today have disappeared? What will continue producing light when the great age of stellar brilliance begins to fade? Because somewhere in the far future cosmos, a handful of surviving sources may become the last beacons illuminating an increasingly dark universe. When we look into the night sky today, it is difficult to imagine a universe running out of light. Every direction reveals stars. Entire galaxies shine across the darkness. Nebulae glow with color. Quasars blaze from unimaginable distances. The cosmos appears overflowing with illumination. Light seems so abundant that it feels permanent, as though the universe itself is designed to remain bright forever. Yet the brilliance we witness today belongs to a particular chapter of cosmic history. The universe has not always looked this way. More importantly, it will not always look this way. The age in which countless stars fill the heavens is temporary. It occupies only a portion of the universe's lifespan. Long after humanity is gone, long after Earth has disappeared, and long after many familiar galaxies have transformed beyond recognition, the cosmos will continue evolving toward a future where light becomes increasingly rare. This realization leads to one of the most fascinating questions in cosmology. When most of the familiar sources of illumination have faded away, what will still be shining? What will become the final beacons of light in an aging universe? To understand the answer, we must first recognize that stars are not eternal. Every star survives by converting matter into energy through nuclear fusion. Deep inside stellar cores, hydrogen is transformed into heavier elements. The process releases enormous amounts of energy that eventually escape into space as light. This mechanism powers the sun. It powers the stars visible tonight. It powers much of the illumination that fills the observable universe. Yet fusion depends on fuel. A star can shine only as long as material remains available to sustain the reactions occurring in its interior. That fuel is consumed. The star changes. Its structure evolves. Its future unfolds toward an ending determined by its mass and composition. Some stars live for only a few million years. Others survive for billions. Even the longest-lived stars eventually exhaust the resources that make their brilliance possible. The future universe therefore faces a gradual decline in stellar illumination. This decline does not happen suddenly. There is no moment when the stars simply switch off. Instead, the process unfolds across timescales so vast that ordinary human intuition struggles to comprehend them. The first major transformation involves star formation itself. Today, galaxies continue producing new stars because enormous reservoirs of gas still exist throughout the cosmos. Clouds of hydrogen collapse under gravity, new stellar systems emerge, fresh sources of light enter the universe. This process cannot continue indefinitely. The supply of available gas gradually decreases. Each generation of stars consumes part of the remaining material. Over immense spans of time, galaxies become less efficient at producing new stars. The birth rate declines. The cosmic population ages. Eventually, many galaxies will contain mostly older stars rather than newly formed ones. The universe enters a different era. The brilliant activity associated with youthful galaxies begins to fade. The cosmos remains illuminated, but much of its light comes from aging stars nearing the final stages of their existence. Among the most important survivors of this future age will be red dwarf stars. These small stars are remarkably different from larger stars like the Sun. Because they consume their fuel extremely slowly, they can survive for astonishingly long periods. Some theoretical estimates suggest lifetimes measured in trillions of years. To appreciate how extraordinary this is, consider that the current age of the universe is roughly 13.8 billion years. A trillion years is vastly longer than everything that has happened since the Big Bang. Long after larger stars have disappeared, red dwarfs may continue shining. They may become the dominant sources of illumination throughout much of the future cosmos. Entire eras of cosmic history could pass while these small stars quietly continue their slow nuclear reactions. Yet even red dwarfs are not eternal. Their fuel supplies diminish. Their light fades. The universe continues moving toward darkness. What remains after the age of stars begins to end is one of the most intriguing questions in astrophysics. The answer involves objects that do not shine in the same way ordinary stars do. White dwarfs, for example, represent the remnants of stars that have exhausted their nuclear fuel. These dense stellar cores no longer generate energy through fusion, yet they remain hot. For immense periods of time, they radiate stored heat into space. Imagine removing the flame from a piece of metal heated in a furnace. The metal continues glowing long afterward because it retains thermal energy. White dwarfs behave similarly on cosmic scales. They become fading embers of an earlier age. For trillions of years, they may continue releasing faint light into the darkness. Neutron stars provide another source of future illumination. Formed through the collapse of massive stars, these extraordinary objects possess extreme densities and powerful magnetic fields. Although they gradually cool, they can remain detectable for immense periods. The future universe may contain countless stellar remnants quietly radiating energy long after ordinary stars have become rare. Black holes introduce an even stranger possibility. For much of scientific history, black holes seemed completely dark. Their gravity is so intense that not even light can escape once it crosses the event horizon. Yet, modern physics reveals that black holes are not entirely silent. Through a process known as Hawking radiation, black holes may slowly release energy over incomprehensibly long timescales. The larger the black hole, the slower the process. Some supermassive black holes could survive for periods so vast that the current age of the universe becomes insignificant by comparison. Long after stars have vanished, black holes may remain among the final sources of detectable radiation. Their light would be unimaginably faint. Their timescales would be almost impossible to comprehend, yet they would contribute tiny traces of illumination to the far future cosmos. What makes this progression so fascinating is that the universe gradually shifts from bright, energetic sources to increasingly subtle ones. The early cosmos contained vast populations of active stars. The later cosmos relies on stellar remnants. The distant future depends upon the slow release of stored energy from ancient structures. The character of illumination changes. The brightness declines. The silence grows. Another important factor involves cosmic expansion. As the universe grows larger, the light emitted by surviving sources becomes increasingly stretched. Wavelengths lengthen, energies decrease. Even photons that continue existing become more difficult to detect. This means that the future universe experiences two transformations simultaneously. The production of new light decreases. Existing light becomes increasingly diluted. The cosmos gradually transitions from brilliance toward faintness, yet complete darkness remains surprisingly difficult to achieve. As long as any process releases energy, some form of radiation continues to exist. A single surviving photon still represents a trace of illumination. A cooling stellar remnant still contributes energy to its surroundings. A black hole slowly evaporating through Hawking radiation still participates in the story of light. The universe therefore approaches darkness asymptotically. It moves toward it without necessarily arriving all at once. The most profound aspect of this future is that the last sources of illumination will serve as relics of earlier ages. They will preserve evidence of stars that once blazed across galaxies. They will carry traces of cosmic structures that formed billions or trillions of years before. They will act as final reminders that the universe was once filled with extraordinary brilliance. In that distant future, every surviving source of light becomes precious. Every photon carries history. Every faint glow represents endurance. Every remaining beacon stands as a witness to an earlier cosmos overflowing with radiance. And as the number of luminous objects continues to decline, an even deeper question emerges. If the universe keeps aging, if stars disappear, if stellar remnants cool, and if even black holes eventually fade, what happens to the final surviving photons still traveling through space? Will there come a moment when the very last photon reaches the end of its journey? Or can light continue existing even beyond the final age of cosmic illumination itself? Whether the final photon will ever reach the end of existence. Among all the questions raised by the fate of light, none reaches further into the future than this one. What happens to the final surviving photon? After stars have exhausted their fuel, after galaxies have drifted beyond contact, after black holes have completed their unimaginably long lives, what becomes of the last remaining traces of light still moving through the cosmos? The question sounds simple. Every journey seems like it should have an ending. Every traveler appears destined to arrive somewhere. Human experience teaches us that motion usually leads to a destination. A ship reaches a shore. A train arrives at a station. A message eventually finds a recipient. Photons challenge that intuition. A photon does not travel because it is trying to arrive. It does not possess a destination built into its existence. Once created, it simply moves through space-time according to the laws of nature. Whether it encounters a planet, strikes a detector, collides with a particle, or continues onward through empty space depends entirely on the universe it inhabits. This distinction becomes crucial when we imagine the far future. The future universe is expected to be very different from the cosmos we know today. The brilliant galaxies filling modern telescopes will not remain unchanged forever. Star formation will gradually decline, existing stars will age, stellar remnants will cool, cosmic structures will become increasingly isolated as expansion continues stretching the fabric of spacetime. The universe will not suddenly switch off like a lamp. It will slowly drift into a condition where sources of illumination become increasingly rare. As this process unfolds, the population of photons traveling through space will continue evolving. New photons will become less common. Ancient photons will become more important. The surviving light crossing the cosmos will increasingly consist of travelers released during earlier eras. Imagine walking through an enormous library after most of the books have already been removed. The remaining volumes suddenly become more significant because they preserve information from a richer past. In a similar way, the final photons would become relics of a universe that was once crowded with stars and galaxies. Yet even these surviving travelers face a changing environment. The expansion of the universe does not stop. As space-time grows, wavelengths stretch. As wavelengths stretch, photon energies decrease. This process continues regardless of how old the photon becomes. A beam of visible light can become infrared radiation. Infrared radiation can become microwaves. Microwaves can stretch into radio wavelengths. The expansion keeps working. The photon survives. Its energy becomes increasingly diluted. This raises a fascinating possibility. The final photon never truly disappears. It simply becomes more difficult to recognize. Imagine hearing a sound that grows quieter over time. The sound may not stop suddenly. Instead, it fades gradually until it becomes impossible to distinguish from silence. The vibration continues, but the listener can no longer detect it. Something similar may happen to light. A photon can persist while its wavelength becomes larger and larger. The traveler survives. Its ability to influence the universe diminishes. The deeper we explore this idea, the stranger it becomes. Human beings often think of endings as events. A star explodes, a civilization collapses, a structure breaks apart. The ending is visible and identifiable. The fate of light may not involve such a moment. The final photon might never encounter a dramatic conclusion. It might simply continue existing while the universe around it becomes increasingly empty, increasingly cold, and increasingly vast. One of the most remarkable aspects of this possibility comes from the nature of photons themselves. Unlike unstable particles that eventually decay, photons are currently believed to be stable. No experiment has ever demonstrated that a photon possesses a finite lifetime. As far as modern physics can determine, a photon can continue existing indefinitely unless it interacts with something. This means that the survival of light may depend more on the future of the universe than on the properties of the photon itself. If the universe provides no obstacle, the journey continues. If the photon encounters nothing capable of absorbing it, the traveler remains. This realization creates an extraordinary image of the far future. Imagine a cosmos where almost everything familiar has vanished. The great stellar civilizations of the universe belong to the distant past. Galaxies have become isolated islands separated by unimaginable distances. The energetic activity that once filled space has largely faded away. Yet somewhere in that immense darkness, photons still travel. Ancient messengers continue crossing space-time. The universe grows older. The journeys continue. Another fascinating question emerges when we consider whether the universe itself has an ending. The answer remains uncertain. Modern cosmology offers several possibilities for the ultimate future of reality. Some models suggest eternal expansion. Others explore more exotic scenarios involving transformations of spacetime on scales beyond current observation. The details remain unknown. Because the future of the universe remains uncertain, the ultimate fate of the final photon remains uncertain as well. If the cosmos expands forever, the photon may continue traveling forever. Its wavelength may become increasingly stretched. Its energy may become increasingly small, yet the journey itself could persist without limit. In that scenario, the final photon never reaches an ending because the stage upon which it travels never ends. The traveler survives as long as space-time survives. Other possibilities introduce different outcomes. If the structure of the universe undergoes profound changes in the far future, the fate of light would become tied to those changes. The destiny of photons cannot be separated from the destiny of reality itself. This is what makes the question so profound. Asking about the final photon ultimately becomes a way of asking about the future of existence. The two stories become inseparable. What happens to light depends on what happens to the cosmos, and what happens to the cosmos remains one of the deepest mysteries in science. The most beautiful aspect of this question is that it transforms light from a familiar phenomenon into a cosmic witness. Every photon released today may participate in a story extending far beyond the lifespan of stars, planets, and civilizations. A beam of light leaving a distant galaxy tonight could survive through eras of cosmic history that no observer will ever witness. It may cross regions of space that have not yet formed. It may travel through futures beyond imagination. It may continue moving long after the structures that created it have vanished. The final photon is not merely a particle. It is a symbol of endurance, a reminder that traces of the past can survive into unimaginably distant futures. A traveler carrying echoes of ancient stars across an evolving universe. And when we ask whether the final photon will ever reach the end of existence, we encounter a remarkable possibility. There is no final destination waiting in the darkness. The ultimate fate of light is not arrival, but continuation. A silent journey through an ever-expanding cosmos, carrying the last surviving memories of a universe that once blazed with countless stars, countless galaxies, and an endless flood of light stretching across the depths of time. Every photon carries a story. Some began their journey in the hearts of stars that no longer exist. Some were released by galaxies that have drifted beyond reach. Others have traveled across billions of years of cosmic history, crossing an ever-changing universe without pause. Yet the fate of light is tied to the fate of the cosmos itself. As space continues to expand and the universe grows older, even the brightest traces of existence are stretched, scattered, and carried into a future unlike anything we know today. The question is not only whether light ends, but what its endless journey reveals about reality. Somewhere in the darkness of the far future, the last surviving photons will continue their silent voyage, carrying the final echoes of a universe that once blazed with light.